early slash late Friday night. Welcome to the live. Thank you so much for joining. Kitty cats are in a bit of a playful mood right now, so you might see some zoomies happen. Here we are. We are live. This is our Friday Physics or Physics Friday Live. Thank you so much for joining again. Thank you so much for watching. If you're watching this as a video upload later on, and we will be getting our party started. Look at this, my water is already boiling. So tonight I made some arrangements already. I already had my food. Where are you, Suji? Good, hi. I already had my food. The water is already bubbling. I am well underway with making the tea. Suji already had one round of zoomies. Baji has his eyes mostly closed. So I think we're well underway. We're just happy to be here and we're ready to catch up with everybody and we're ready to get this physics party started. How are you? How is everybody doing? Say something in the chat when you join so that I know you're here and saying hi. And we will get this physics party rolling. Thank you once again for being here. Yay! Oh, Baji, you're so cute. Baji is looking extremely cute. He will give you company as I go make my tea slash Horlicks, and I will bring it over here on the sofa. So we will sit together and we will talk about physics and kitty cats. And welcome, welcome. Who's joining? Yay! Oh, Baji. Baji's closing his eyes. Little Baji's eyes are closing because he is busy with a nap. So, there. Give me 1 second. I'll bring my tea over and we will sit. Okay. We hope to meet many friends today. Both the old ones as well as the new ones. So, thank you, thank you. I'm going to share the live before I forget. Hello. I'm going to share the live before I forget. Hello. How are you? How is everybody doing? Hello, my lovely friends. Hello, hello, hello. We are here. Oh, sorry. That's a big noise. We are here for Physics Live. Yay! Hi. Hello. Hi. We are live. So I'm just putting it on my channel as well. We are ready to get going here. Oh my goodness, Baji. Baji. Your friends are appearing one by one. Join us, and we will be hanging out for a while. Oh my gosh, oh gosh. Where is everybody? Where are all your friends, Baji? Where are all your friends? Okay, I'm gonna go make the tea. Baji, continue to give everybody company, okay? Oh. Okay, so I'm gonna make my tea and wait for everybody to join. And then we will get this party started and we will get rolling with everything that we're doing. And today, depending on the response we get on the live, I think we will be covering some very interesting topics. right. How is everybody doing? Say something in the chat so that we know you're here and that we are ready for the show to begin. The physics chats to begin. So, Baji, who is here? Hi. Hi, Mako. Cat is the meaning of life. Hi, Lo-Fi88. Hello. Baji, say hi to Mako and hi to Lo-Fi. Everybody, say something in the chat and we'll give you a shout out. We'll catch up with everybody and then we'll get the party started. In fact, this party is already started. How are you guys doing? Cat is the meaning of life. Yes, indeed. Yes, indeed. Okay. Oh my gosh, look at Suji. Suji, what are you doing? Hi, Suji. Suji has found something. Suji? Suji baby corner, Shana? Let's not do that. Let's not. Let's not. Sachi? What are you up to? She is getting into all kinds of trouble. Who ate a snack just now? Who got a snack? Very recently. Very recently. Who got a snack? Alright, I'm making my tea and then we will all sit down and settle down here. Kitty cats have gotten into a lot of trouble today. They have done all kinds of things. All kinds. Ish, baba. I spilled some of my tea. Oh my god. Ish. I don't like to waste my tea. Oh no. Alright. Thank you for being here, everybody. Give me one more second. Let's gather. Let us gather around. Okay. You're okay. You've had your snack, baby. You've had your snack. Let's go back to Baji. He's being a good boy at the moment. He's being a much more good boy at the moment. All right, everybody. Off and off and off and off and off and off. Good. So, how is everyone doing? Tell us in the chat. We will be over here. And we will be discussing some interesting topics. Oh my gosh. Oh my gosh. So, we're back on this live. We actually went live earlier today. But this is our typical Friday Physics Live. And we're hoping that many people can join us for this. There is currently... Sachi? Oh, Sachi, are you crying? Sachi is getting zoomies and she even let out a cry. So I'm gonna check on her. What's wrong, Sachi? Kiyoji, mama? What's wrong, Sachi? She wants a snack. But the thing is, you've already received many snacks. What's wrong? You seem very excitable. What's wrong? Look at how many bowls. I gotta clean up in this area. But I wanna do the live right now and then clean up. I think Baji's gonna have zoomies too. Okay, yes, Suji is just having zoomies. Okay, that's fine. We will watch her zoomies. Kiyoji, Suji. Suji! Actually, I think she wants to play. Let me do that for a second here. She wants attention and acknowledgement of her struggles as a zoomie kitty. See, if I get up, she always thinks that it is to feed her. Suji, what if I wanted to play with you? What if I wanted to play? Oh, Suji, you're so cute. Oh, actually, you know what? We'll get their zoomies figured out is the laser pointer. Okay, guys, there's a change of plan. We will be playing with the laser pointer because kitty cats are being very, kitty cats are being very energetic and we will do this instead. Look at that. What is that? What is that? What is that? Hello? What is that? Oh my gosh, what is that? Oh, Suji mama, where is Suji? Where is Suji? Where is Suji? Suji, what's this? Suji, you were having zoomies, so mama decided to play. We're gonna turn this light off. What is that? What is that? What is that? Oh my god. What do we have here? What do we have here? Oh my god. She had so much zoomie that she even cried. Hello? Hello? Oh my gosh. Suji! Suji, do you want to run? Do you want to run? Suji. Baji, I'm going over here. I'm going over here. I'm going over here. We're coming this way. They can't see it very well if the lights are not off completely. Yes. He can chase it. He still chases it. He's gonna chase it. So Suji mama was sad. Oh my gosh, Suji. Suji! Suji has collided with the door. Are you okay, Suji? Oh my gosh, Suji, what's wrong? Suji mama? Are you okay? Oh my god, oh my god, wow. Wow, wow, there is a commotion here from the kitty cats playing. They have full-on zoomies. I was gonna do a peaceful, soothing live and physics chats, but we're doing this because there is a much-needed zoomie happening here. Hello, oh, there you are. I was wondering where you were. Okay, all right. More zoomie? More? Okay. Hello. Suji ran so fast that she collided with the door. I was quite afraid, but it seems all in a day's work for her. All in a day's work. Oh my God, oh my God. Sometimes they scare me with their rapid collisions. Okay, how are you guys doing? How's everybody doing? This is like a Korean drama right here. I don't know why I said that. It's just dramatic, that's all. Hello. Oh my gosh. I feel like it all started with Suji's zoomies. Once she had zoomies, we had to do something. We will go back to the physics live, I promise. You know, sometimes I start the live thinking one thing and it ends up being something else. Sometimes we have a soothing live and sometimes we have zoomies. Sometimes we think we will just chat normally and then we end up talking about relativity. So you really never know. It's live action drama. Don't hold it against us. Live action. No, no, no. Maybe I'll sing for you guys as an added entertainment. Da, 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 da. Look at Suji. She's over here. In the corner. In the corner. We are a bunch of dramatics in this family, myself included. Hope you're enjoying. Say something in the chat. Say something in the la 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 la. Oh my God. Okay, also, where are all my physics friends? Nobody seems to be here for the physics people, for the physics topics yet. If you're here, please let yourself be known because it's rather lonely right now. Say something, na 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 na. Okay, I think we're good. I think the zoomies are done for now. So, all right. So we have been, in fact, covering a lot of interesting topics. So, including but not limited to 20th century modern physics as well as 21st century physics. So, I thought that it would be good to continue to do that on especially the Friday Physics Lives. And I have a bunch of topics that I've been touching upon. We talked about dark matter candidates, I think it was a couple of days ago, and that was a really interesting discussion. So I think we can continue on in that direction here today. So what I'll do is I'll give you some options and you can let me know from your feedback. We can figure out what is happening. Whether we will cover some cosmology today or whether we will do something with my thesis today. Some people have asked about that too. So I will let you all appear and give me some feedback, and I'll give you some a few moments here and we can also get started. I will take some sips of my tea probably, but basically I wanted to touch upon this concept of the expanding universe with this book. So this is Modern Cosmology by Scott Dodelson. I introduced the book last time, a couple of days ago. And we talked about how dark matter, when we talk about really the most biggest open questions of the universe today, really the number one most big and open question is the nature of dark energy. And I was mentioning how dark energy is really sort of a cosmological type of question. It has to do with the expansion of the universe. Remember how we touched upon this topic earlier when we said, when we were talking about general relativity being worked on by Einstein in the early 1900s, 1920s or so. Actually, maybe some of it was even sooner, 1917, 1919. Those were some really fantastic years of development in the direction of relativity and also general relativity, giving us the updated and more correct form of gravitation. But because he was also faced with this incredibly difficult challenge of stabilizing the universe in the face of this attractive force of gravity, Einstein was wondering, just like anybody else, how the universe can be stabilized. If everything is just under gravity, then the universe should have collapsed on itself. But it doesn't. The universe does not collapse on itself, so he introduced the cosmological constant as a placeholder to stabilize the universe in his equations. Later on, over 100 years later, now, in today's date, we still don't really understand what this cosmological constant comprises. And back in the day, even during his time, we called it something like dark energy or the energy of the vacuum, something that is making the universe actually stable. He reluctantly introduced the constant, expecting it to stabilize the universe. He reluctantly, because he didn't really know what it was, but he had to do something. So in his equations, he put a placeholder there, called it the cosmological constant. We still call it the cosmological constant. That name has stuck. And turns out that it has become into a much bigger question now as we continue to explore in this area. And we found that the universe is not only stable against gravity, it is in fact expanding. And it's not only expanding, it is in fact acceleratingly expanding. Its expansion is accelerating, but confirmations of something like this, the fact that it's acceleratingly expanding, did not come until much later, sort of in the 1980s or so. I believe the year was 1989 when more confirmation in this direction came with our work and with our greater ability to experiment, measure, and observe the universe with better and better instruments. So Hubble was somebody we must all thank for a number of such amazing observations. Hubble gave us more galaxies and the fact that our galaxy is not the only galaxy, that there are other distant galaxies. And in fact, they're depending on where you're looking, the universe seems to be expanding. And the expansion is accelerating. So that's what brings us to the nowadays current date question of dark energy, which is yet to be solved, as in we still don't know exactly what is dark energy. So that is the number one open question, because it turns out that most of the energy of the universe is dark energy. Most of the stuff of the universe is dark energy, followed by dark matter. There's also this other open question. I was going to say, out of the two most biggest open questions, the number one is dark energy. What is it? And number two is dark matter. What is it? We have covered some dark matter candidates in the channel already during our past live streams, and we've been mentioning about dark energy. We've been saying how dark energy is also something very important, comprises a large portion of what makes up the universe, but we don't understand exactly what it is. So in order to delve into these topics, I wanted to also share that dark matter, the way we're approaching it, and in fact, how we can approach it really is more of within the field of astronomy and particle physics. So far, what we saw about dark matter is within the realms of astronomy and particle physics. In those subfields, if you, try to do an experiment that gives us some particle nature, gives us the particle nature of dark matter by discovering that particle in some sort of environment or some sort of experimental conditions, that is sort of a particle physics type of approach or particle physics type of experiment. Of course, all these subfields have a lot of overlap. Astronomy would be where, say, maybe you take measurements and observations of what's happening in our own galaxy and even the nearby galaxies. And maybe, say, for example, remember there was a dark matter candidate called Macho, which stood for something like massive compact halo object. So the thought was that if dark matter is so dark slash invisible, what if it was something that was just very dim and it did not contribute much to luminosity? So we don't really know that it's there, but it's actually there. Maybe there's compact objects in our halo of our galaxy which comprise dark matter. So this was a candidate that we actually talked about. But then later on, we concluded in the same text that actually they would only comprise 20% of the dark matter in our galaxy. So we can't really say that we have solved dark matter. But for example, something like the Macho, say somebody, if people were seeking that, then that would be more of an astronomy problem. Today, we're going to spend some time with cosmology because it is something we have not talked too much about. We've mentioned it here and there, especially in the context of Einstein's work, of course, kind of gave birth to cosmology in some sense, general relativity, and sort of this cosmic description of nature that is given by Einstein's general theory of relativity is really what's birthing this field of cosmology. Okay, and see how it's called modern cosmology. Well, I don't know if there is much cosmology that's not modern, because cosmology as a field really kind of developed in the last 100 years or so, especially since we got Einstein's equations. So maybe I'm wrong and there is some old cosmology that I know not of, but or maybe this means sort of even more modern than the 1900s. But basically, before the 1900s, we didn't even know that there were other galaxies. So I'm not sure what cosmology really we could have done then, because cosmology is much more to do with the universe scale or cosmic scales than it has to do with just our galaxy scale or sort of the neighboring galaxies scale. Basically, if we have a neighboring galaxy, our solar system, our galactic center, stuff that's happening in the center of our galaxy, for example, that's not really cosmology, that's more astronomy. You know, I mean, they are all overlapping fields once again, but cosmology is when you're really understanding the age of the universe, how the universe started, this expansion thing about the universe. All that is in the realm of cosmology, and understanding it at a much more this bigger and fundamentally kind of way. Hello, just joined. Honestly, what is cosmology? I really don't know. That's a great question. That's exactly what we are after. That's what I've been trying to kind of describe. So, let's see what this author says. I don't know if he actually defines cosmology. Cosmology is basically the study of the universe at a cosmic scale. So I was giving you, I'm just kind of describing it through examples. I was going to say that, say, if you're, say, studying some object in the sky and it's sort of in our galaxy or a neighboring galaxy or something like that, that's more of an astronomy thing. But if you discover something that helps you to understand our universe better, an example of it would be to learn about the expansion of the universe, for example. So the scales would be much more larger. That's more in the realm of cosmology. As we kind of start to reference the book too, I think you will get a much better feel for it. But yeah, cosmology is different from astronomy and particle physics and things like that. We will also look at a dark matter candidate that is given to us by cosmology. It's called cold dark matter. So notice that when we studied dark matter candidates from the astronomy book, because I referenced an introduction to astrophysics book, so more of an astronomy, astrophysics-y type of book, earlier in my earlier lives, and we talked about dark matter candidates. So after this live, you can always go and find my earlier lives too, where we have talked about what I'm talking about right now in more detail. Okay, and you can see that I've been in school for a very long time. I'll tell you in just a moment. So you will see what I'm talking about. But those were sort of an astronomy approach to dark matter. Here in this book, this is a more cosmology approach to dark matter, okay? And once again, something like dark energy and understanding dark energy is a cosmology topic. Something like dark matter can be a both cosmology or astronomy or particle physics topic, depending on the approach you're taking. So there's much more room there, if you will. Okay, so let's see what the author says. So this is a textbook. It's called Modern Cosmology by Scott Dodelson. The textbooks that I cover during my live sessions, during my live streams here on the channel, I always tell you what they are. They're generally textbooks that are taught at universities, and they're usually the textbook of the class taken by the physics majors or astronomy majors or astrophysics classes, things like that. So the information should be really solid. It should be something that's already kind of established and not something that is still being, conjectured upon. So let's see. Does he actually define cosmology? I'll read the preface for you here. Let me answer your question. What school did you go to and for how long? So, well, I went to South Point and South Point High School in India since the age of 3 to 18. So that was my, primary schooling until high school, class 12, 12th standard. Then I went to NC State, North Carolina State University for my bachelor's degree in physics. I also pursued other topics, but physics is the one I finished. Didn't have time to pursue all my different various interests and majors that I wanted to do, and minors. I also got a math minor there. I pursued some other things that I did not finish. But I did physics with honors at NC State. Then I went to Ohio State University for my PhD. There I got my master's in physics and PhD also in physics. And that was 5 years. So I've been in school for physics for 9 years, and I've also worked in a related field that, utilizes physics for 6 years. So now I've been doing all this stuff for 9 plus 6, 15 years. So that's where I am at. 15 years only. Not long, given the length of a normal career in physics. So there are two aspects of cosmology today that make it more... Oh, snap, sir, you're a citizen now? Yeah. Yes, I am. But yeah. So I don't know what this quote is. I will skip it. But the preface of this book starts as, there are two aspects of cosmology today that make it more alluring than ever. First, there is an enormous amount of data. To give just one example of how rapidly our knowledge of the structure of the universe is advancing, consider galaxy surveys, which map the sky. In 1985, the state-of-the-art survey was the one carried out by the Center for Astrophysics. It consisted of the positions of 1,100 galaxies. Today, the Sloan Digital Sky Survey and the 2-degree field between them have recorded the 3D positions of 500,000 galaxies. So that's cosmology, getting data and utilizing data from so many galaxies for one, to better understand the universe. So cosmology is to better understand the universe. It's not just about one object. It's not about finding Earth-like planets. It's not about finding more suns of other planets. It's not about the galactic center of our own galaxy. It's not even about our neighboring galaxies and the dark matter that there may or may not be there. I think there is there. Those are not cosmology. That's astronomy or astrophysics. Cosmology is really about the entire universe. So it's very simple. We just care about the universe when we talk about cosmology. But you will see how when you talk about everything, the theory of everything, then you are forced to kind of simplify things, actually. Like it's almost like when you don't care about the nitty gritty, when you don't care about stars and planets and comets and asteroids and solar systems and finding other Earth-like planets and Jupiter-like planets and aliens and, black holes. suddenly you care about it in a broader way. You don't care about these specifics. These are specifics, right? These things that I all just mentioned are specifics within the universe. These are interesting too. I love all of these as well. These are astrophysics, these are astronomy. But what about the universe as a whole? How did we come to be? How did we start? How did the universe start? The Big Bang, all those like early type of things. Because honestly, at this point, the universe is more enriched, right? We are here. We're complicated beings. So, I mean, and we weren't there always. Cosmology is more kind of like back to the basics. Like, how did it all begin? What are some of the stages of evolution of this universe? Not just, because we've talked about, for example, stellar evolution. That's the evolution of a star. That's one object, right? It's so specific. Cosmology is about the entire universe. Wait, so cosmology is a type of physics, but more focused on big picture astronomy. Um, yeah, something like that. I wouldn't call it astronomy. It's its own field. Uh, so I wouldn't call it astronomy. Cosmology is study of the universe. Um, there's overlap with astronomy, but I wouldn't. It's big picture understanding of the universe at a cosmic scale. Um, it's more big picture stuff than astronomy. Astronomy is its own thing. It has lots of overlap, of course, with astronomy, but it's its own field. So it's not and yeah, these are basically cosmology is a subfield of physics, I would say. Astronomy generally tends to have its own identity. So, like at Ohio State, for example, again, these are only, we're talking about definitions, so it doesn't really matter. But I'll just say that at Ohio State University, the Department of Physics is separate from the Department of Astronomy. If you're doing astrophysics type of things, you'll probably have a lot of overlap. And there's this thing called Center of CCAP, Center of Cosmology. Wait, CCAP. What's the C? Center of. Maybe it is cosmology. Center of Cosmology and Astroparticle Physics, maybe. Whatever. Basically, there's a center that kind of unifies the Department of Physics and the Department of Astronomy, because traditionally, astronomy has been separate from physics. Now, of course, there's so much overlap that maybe it doesn't make sense for them to be so separate. But astronomy, also remember, is a very old field. Like astronomy is probably older than physics, right? So this is why a part of it is also how things have developed. You know what I mean? Like astronomy as a field might want to make themselves separate from physics, but of course astrophysics and astronomy have a lot of overlap. But condensed matter physics might not have too much overlap with astronomy, and so physics department is kind of separate from astronomy. In some schools they're not separate. Like at NC State, where I went for my bachelor's, it wasn't separate. It was the same department. But in some larger schools and larger departments, they can even be two separate departments. Okay, and cosmology is definitely is usually under the physics department. So yeah, it's a subfield of physics. And so actually now I remember something about like why the author is distinguishing cosmology as modern cosmology. Basically, what has happened now is what he just said in the paragraph I read out earlier. Now we have a lot of data. We didn't have this much data 100 years ago, or even, I don't even know, 50 years ago. Like we just have so much data now that modern cosmology is really about the quantitative study of the universe. It's no longer just a theory. Like basically, general theory of relativity by Einstein was a theory, and it wasn't really confirmed until, subsequently. At this point, cosmology is not just a theory that's, people are theorizing something and then you never have a way to confirm it. We're now well on our way to confirming things and measuring things. So basically what they're trying to say is cosmology has, basically cosmology has come a long way. You've taught me up on dark matter, but what is dark energy? I don't know your plan for this live and don't want to derail it. No, no, no. This is a good question. My plan for the live is to talk about dark energy. I wanted to give an overview of all the different fields, but you're right. We are going to talk about dark energy. So, okay. So, we will talk about dark energy. What is dark energy? So, I mentioned earlier that the real history of dark energy is really that cosmological constant that had to be introduced in order to stabilize the universe. And later on, we found, so this was done by Einstein, remember, when we talked about Einstein's cosmos and Einstein's work from the other book that we were referencing by Michio Kaku. And we read in some other textbooks as well. Basically, this cosmological constant that had to be introduced by Einstein in his equations to stabilize the universe, and to basically prevent it from collapsing on itself under gravity. This has become very important now because it has led to this concept of dark energy, or the energy of the vacuum. There is something, and we don't know what it is, which is making our universe expand. And not only expand, it is making our universe's expansion accelerate. Okay? So maybe some people just don't care about this because what they care about is not affected by this, because this would be obviously a more larger scale kind of thing. But cosmologists care about this. Basically, if you care about this issue, you're a cosmologist. If you want to work on this, you would be doing cosmology. That's what this field is, okay? Like basically, this universe is how our universe is evolving, its expansion, what our universe is doing at a large scale. That is cosmology. So we will get into it a little bit here. Einstein's discovery of general relativity is in the last century. So see, a lot of the things we will discuss now, we have kind of touched upon already. So this should be like a review, but hopefully it'll kind of refresh your memory as well and reaffirm some of the things we've learned. So we will now start with this first chapter of this book, and it's called The Standard Model and Beyond. And this first part should kind of help you with the topic that we will discuss today. Einstein's discovery of general relativity in the last century enabled us, for the first time in history, to come up with a compelling, testable theory of the universe. The realization that the universe is expanding and was once much hotter and denser allow us to modernize the deep, age-old questions. Why are we here? And how did we get here? The updated versions are now, how did the elements form? Why is the universe so smooth? And how did galaxies form from this smooth origin? Remarkably, these questions and many like them have quantitative answers that can be found only by combining our knowledge of fundamental physics with our understanding of the conditions in the early universe. Even more remarkable, these answers can be tested against astronomical observations. So there will be plenty of astronomy too in this field, but basically the fact that our universe yeah, so is dark energy not something we have observed, unlike dark matter? Well, we have observed the expansion of the universe, and also we have observed that the expansion is accelerating. So in that sense, we have observed evidence of dark energy really as much as we have observed evidence of dark matter. Two different things, but basically we do have evidence of both, in the sense of that, yeah, there is something going, there's something, but what that is, it could be, they're two very different things, because dark matter, we assume, or, depending on who you talk to and who, the type of researcher and the particular candidate of dark matter that they are working on, will tell you that dark matter might be a type of particle that we are yet to discover. It might be, something like the compact object that we were talking about, the macho thing. So dark matter is a thing. Basically, it's more of a thing. We don't know what it is, but it's considered to be a thing with mass and everything. Dark energy is almost like a behavior of the universe, and we also don't really know what it is, but and it's not just a behavior. It's also some kind of energy, something that is making the universe expand. It's sort of a behavior. It's sort of an energy thing, but again, we don't know why it's behaving that way and where this energy is really coming from. Yeah. So both we are in the dark about. So we call them dark energy and dark matter. But there are some more specific ways of attacking this question, which we will get into in this chapter. So this why are we here thing, why are we here? We are people. You, me, cats, trees, we're made of elements. So origin of elements I mentioned probably in some of my lives earlier. Actually, the top 3 questions of the universe are what is dark energy, what is dark matter, and what is the origin of all the elements. Now, we know that elements are formed in stars. What the stuff of that we are made of. You, me, why are we here? This question, right? Now, philosophically, why are we here? I don't know. But as far as the stuff that we're made of is, these elements that we're made of, those are made in stars. We know that now. And many of the elements we understand very well how they're made in stars, or at least we have pretty good ideas about them that are pretty compelling, as in we're quite confident. For example, the sun makes helium out of hydrogen. So we know for a fact, okay, the sun makes helium. That's pretty much what the sun is doing for the most part. There are some other elements too there, but mostly it's converting hydrogen into helium. Depending on the particular star, it could make other things. It does make. We are all coming from star stuff. All the elements that make up our bodies, this earth, the cats, the trees, everything came from a star's death, pretty much. Because when a star dies, it spews all this matter into the space, and we end up somehow here. So basically, how did we get here is related to how elements were made. And the fact is that there are some elements that we still don't know how they're made, and that's why I said that it's the third top question. But we will also get into this dark energy and dark matter thing here, because why is the universe so smooth? You will see what they mean by that. How did galaxies form from this smooth origin? Basically, the universe has been observed in the past to be very homogeneous and smooth. So if it were so smooth, why did something like galaxies form even? Why is there this structure? You see what I'm saying? So galaxy formation itself is a question mark in the field of cosmology. We don't just take for granted the universe. We don't just take for granted that galaxies have formed and structure has formed in the universe. We don't take for granted that the universe is expanding when you look at distant galaxies and see that they're acceleratingly expanding, acceleratingly going away from us in the distant galaxies. So these are sort of, these are understood, but in cosmology, we ask why. Basically, we don't take for granted. We ask the question why this is happening. If we have some sort of data that tells us the early universe was very smooth, you'll see what I mean by smooth in just a bit here. But if the universe was so smooth, why do we have galaxies now? What caused that? So those types of questions are answered in cosmology. It's very different from the traditional astronomy view of things. Astronomy, think of it as much more specific. Like they really want to they want to get specific about some object in the night sky, like the moon or a black hole, or something like that. Galactic center, the X-rays that are coming from the galactic center, the gamma rays that might come from some other thing. That's astronomy. That's very specific. But at a large scale, why are we here? how did galaxies form? That's more of a cosmology question. Okay, this chapter describes the idea of an expansion. So now going back to the chapter here. This chapter describes the idea of an expanding universe without using the equations of general relativity. The success of the Big Bang rests on three observational pillars. The Hubble diagram exhibiting expansion. So we know from Hubble that we have expansion in this universe. Light element abundances, which are in accord with Big Bang nucleosynthesis. So light element abundances just means the lighter elements in the periodic table. How much of basically the abundance of them in the universe, how much of it we expect in the Big Bang's nucleosynthesis process, and how much we think there is, it better line up. Because, remember, Big Bang happened and our universe came to be. Galaxies are a much later thing. Stars are a much later thing. So now we know that the heavier element, we call them metals. Pretty much anything above helium is a metal. We know that we are made of elements that are made in stars, but in the beginning there were no stars. There were no galaxies. So whatever was there in the beginning has to have come from the Big Bang nucleosynthesis. So if we have some estimates of, the elements abundances at that time, hopefully we can confirm that. Otherwise, that would be an issue. So, and the black body radiation left over from the first few 100,000 years, the cosmic microwave background. So, this cosmic microwave background radiation is going to be very important as well. Basically, the universe has given us clues in the form of such a thing. From the first few 100,000 years of the universe, we can collect this black body radiation signal. Hi is sure. And that is called the CMB radiation, cosmic microwave background radiation. I had a sort of a magnet, which is basically what the CMB looks like, that I can try to find and show you, but I'm sure there's going to be a picture of it here somewhere. But basically, we'll continue here. After introducing these pieces of evidence, I move beyond the standard model embodied by the three pillars, development in the last 2 decades of the 20th century. So the last 2 decades, so the 1980s and 1990s, both theoretical and observation point to the existence of dark matter and perhaps even dark energy. So we're just recapping what I was saying. Basically, we have theoretical as well as observational evidence for dark energy and dark matter, the need to understand the evolution of perturbations around the zeroth order smooth universe, and inflation, the generator of these perturbations. So basically, they're talking about at the zeroth order, the universe is very smooth, but there are some perturbations around this zeroth order, which leads to more structure in the universe, and we need to understand the evolution of these perturbations. That's what he's talking about. Please show me your cat. Hi, Tia. He is right here. Thank you. Thank you for all the attention. Hi, Tia. Hello, Ishur. So these 3 things is going to be something that we try to understand with cosmology. The expanding universe. We have good evidence. So this is from the book. Okay, so what we are about to read now is from this book. Hi, Tia. I hear you. Let's take a break from the same message over and over. We have good evidence that the universe is expanding. This means that early in its history, the distance between us and distant galaxies was smaller than it is today. So basically, just to define out what we mean by expansion of the universe, so we have collected data. We we have observational evidence of the fact. Yeah, you started talking about it as I asked. Yeah, yeah. So basically, the definition of expansion is that early on in its history of the universe, the distance between us and distant galaxies was smaller than it is today. And we have collected data on that, basically. It is convenient to describe this effect by introducing the scale factor A, whose present value is set to 1. At earlier times, A was smaller than it is today. It's almost like, look at these pictures. It's kind of like that, right? So it's like a co-moving distance. It was like a small box before, but it becomes a bigger box and an even bigger box, and the time is going to the right here. So that's what's meant by expansion of the universe. We can picture space as a grid, like in this figure that you just saw on the live here, which expands uniformly as time evolves. Points on the grid maintain their coordinates, so the co-moving distance between 2 points, which just measures the difference between coordinates, remains constant. However, so the difference between coordinates remains constant. However, the physical distance is proportional to the scale factor, and the physical distance does evolve with time. And we can measure this. So these boxes that you just now saw, the small box to the medium-sized box to the large Amazon box, that's basically picturing this expansion of the universe. The co-moving distance between points on a hypothetical grid remains constant as the universe expands. The physical distance is proportional to the co-moving distance times the scale factor, so it gets larger as time evolves. So we can get into that. If you want a more detailed description of the experiments or the measurements that are done to figure out how we've measured that, we can get into it. But at this point, let's just say that we've measured that it can happen, that it does happen. Basically, it would entail looking at very, very distant galaxies for a very, very long time. And basically, remember how if we look very far into the universe, it's kind of like looking back into the past as well. So there are clever things that people have done to measure this expansion. And and it was actually a very path-breaking type of discovery when they realized that the expansion is not only happening, but it's accelerating. So a Nobel Prize was also given on this. So you could even look that up and see how they exactly did it. In addition to the scale factor and its evolution, the smooth universe is characterized by one other parameter, its geometry. There are 3 possibilities: flat, open, or closed universes. So remember, we kind of talked about this with Einstein as well, with Einstein's work as well. These different possibilities are best understood by considering 2 freely traveling particles, which start their journeys moving parallel to each other. A flat universe is Euclidean. The particles remain parallel as long as they travel freely. General relativity connects geometry to energy. Accordingly, a flat universe is one in which the energy density is equal to a critical value, which we will soon see is approximately 10 to the minus 29 grams per cubic centimeter. Wow. So depending on the density, you actually get this geometry, because in Einstein's equations you have a connection between geometry and energy. If the density is higher than this value, then the universe is closed gradually. Because remember why that this whole thing with Einstein's equations. Einstein basically, general relativity is about gravity, right? It's the updated theory for gravitation. He's basically trying to describe how the universe acts under gravitation. So depending on density is is like a mass type of thing, right? The units of density are some mass divided by volume, right? So gravitation has to do with mass. So imagine that you might imagine that somewhere in the equation is probably something to do with mass and something to do with density, basically. So depending on this density value, you either get a flat or a closed or a open universe. So if the density is higher than this value, then the universe is closed. Gradually, the initially parallel particles converge, just as all lines of constant longitude meet at the north and south poles. The analogy of a closed universe to the surface of a sphere runs even deeper. Both are said to have positive curvature, the former in 3 spatial dimensions and the latter in 2. Finally, a low-density universe is open so that the initially parallel paths diverge, as would 2 marbles rolling off a saddle. So those are the 3 possibilities depending on the density number. Universe is either flat or open or closed. We will read again what flat means. A flat universe is one in which the energy density is equal to a critical value, which we will soon see is approximately 10 to the minus 29 grams per cubic centimeter. Awesome! I'm actually going to go look up some examples of how people have measured the universe and how it explains, then go to bed. Yes. Awesome! Glad you enjoyed. To understand the history of the universe, we must determine the evolution of the scale factor A with cosmic time t. Again, general relativity provides the connection between this evolution and the energy in the universe. So, look at that. This is telling us the scale factor A versus cosmic time. And we know that this scale factor basically has been increasing with as a function of time. So basically they can draw that. So this figure that we just looked at shows how the scale factor increases as the universe ages. So the scale factor gets bigger as the universe ages or as time goes by. Note that the dependence of A on T varies as the universe evolves. So it's not the same dependence throughout, okay? At early times, A is proportional to T to the 1/2, while at later times, the dependence switches to A proportional to T to the 2/3. How the scale factor varies with time is determined by the energy density in the universe. At early times, one form of energy, radiation, dominates. So this is another thing. You will be hearing a lot about the different stages of the universe and how this density is going to be very important. We don't expect, obviously, right, for the density of the universe to be the same throughout. So, and also the form of energy to be the same throughout. There have been changes to this, and that's why we are now in the current state of this older universe, see other things than we would have in the early parts of the days of the universe. So all of this is to be kept in mind. At early times, one form of energy, radiation, dominates, while at later times, non-relativistic matter accounts for most of the energy density. In fact, one way to explore the energy content of the universe is to measure changes in the scale factor. So they can actually measure changes in the scale factor. Wow. We will see that partly as a result of such exploration, we now believe that very recently A has stopped growing as T to the 2/3, a signal that a new form of energy has come to dominate the cosmological landscape. I mean, how cool is that? To quantify the change in the scale factor and its relation to the energy, it is first useful to define the Hubble rate. This is the Hubble rate, h of t, dA dt over A, which measures how rapidly the scale factor changes. For example, if the universe is flat and matter dominated, so that A is going as T to the 2/3, then hi love our toy pups. Then H will be 2/3 over T. Thus, a powerful test of this cosmology is to measure separately the Hubble rate today. So basically, we can try to measure the Hubble rate and see what we're getting and the age of the universe today. So basically, if we measure separately the Hubble rate and the age of the universe, we could try to see what kind of cosmology we're getting. Here and throughout, subscript 0 denotes the value of the quantity today. In a flat, matter-dominated universe, the product H naught T naught should equal 2/3, because they basically think that right now, in this type of universe, well, at that point, it would be going as the 2/3 number. So then you can write down Friedman equation. Now, I'm just going to show it to you. We have discussed this too in the past, actually, when we were covering Einstein's equations. Remember how Friedman had given us a solution to Einstein's equations. So that's what Friedman's equation says, and basically we get a critical density from it, where big G is Newton's constant. So, to use Einstein's equation, we must know how the energy density evolves with time. This turns out to be a complicated question because rho, and rho is for density, is the sum of several different components, each of which scale differently with time. Consider first non-relativistic matter. The energy of one such particle is equal to its rest mass energy, which remains constant with time. The energy density of many of these, therefore, equal to the rest mass energy times the number density. When the scale factor was smaller, the densities were necessarily larger, since number density is inversely proportional to its volume. It should be proportional to a to the minus 1, a to the minus 3. Therefore, the energy density of matter scales as a to the minus 3. So all of this type of math kind of tells us how, if you're able to kind of make a measurement, then you can kind of finagle these, put it into the equation to see how things actually relate. So now let's talk about a measurement. We have actually measured the temperature of the cosmic microwave background. Thank God. So the photons which make up the cosmic microwave background, CMB, today have a well-measured temperature of around 2.725 plus or minus 0.002 kelvins. And there's a paper on this, you can read it. A photon with an energy of kb, T naught, kb is Boltzmann constant, has a wavelength, we would be able to see, we can get the wavelength from that energy. Early on, when the scale factor, so there's equations here that I'm kind of skipping over. Early on, when the scale factor was smaller than it is today, this wavelength would have been correspondingly smaller. Since the energy of a photon is inversely proportional to its wavelength, we know that, right? Like radio waves have less energy than gamma rays, for example. Since the energy of a photon is inversely proportional to its wavelength, the photon energy would have been larger than today by a factor of 1 over A. This argument applied to the thermal bath of photons implies that the temperature of the plasma as a function of time is given by T naught over A over T. At early times, then, the temperature was higher than it is today. So basically, this A is in the denominator here in the equation. Um, yeah, okay. All right. That makes sense though. I mean, when the universe was more early times, uh its temperature was higher. Okay, whatever. That's not too bad. The energy density of radiation, the product of number density times average energy per particle, therefore scales as 8 to the minus 4. So they can do a lot of math based on just very simple things. Isn't that cool? Evidence from distant supernovae suggests that there may well be energy, dark energy, besides ordinary matter and radiation. One possibility is that this new form of energy remains constant with time. That is, acts as a cosmological constant. Remember, as first introduced by Einstein. Cosmologists have explored other forms, though, many of which behave very differently from the cosmological constant. So we actually know some examples of this. Remember how Einstein introduced the cosmological constant because he needed to stabilize the universe against gravity. But then some other people played around with it. And depending on what you call it, you can actually get yourself a different kind of universe, basically. You can play around with the equation. So basically, all of that is to say that there is possibility that the universe is not flat, depending on these numbers. If it were flat, the sum of all the energy densities today would equal the critical density, and the last term would vanish in this equation. If the universe is not flat, the curvature energy scales as 1 over a squared. In most of this book, we will work within the context of a flat universe. So there is evidence, I believe, that the universe is flat. Don't ask me exactly how we know that, but that's pretty much what we believe at this time. So even though there is an ability to consider a universe that's open or closed, depending on the density of the universe, currently I think we believe that it's flat because of evidence. In such a universe, the evolution of perturbations is much easier to calculate than in open or closed universes. So, okay, sounds like the math is easier too. Further, there are several persuasive arguments, both theoretical and more recently observational, which strongly support the flatness of the universe. So even though the mathematics might allow for our universe to be open or closed, basically, right now the observation is pointing towards a flat universe, and there's more evidence of, we can talk about the evidence about this later on, but there is evidence that it's flat. The flat geometry is being supported at this time by the evidence at this time. So okay, this figure illustrates how the different terms vary with the scale factor, while today matter and possibly a cosmological constant dominate the landscape early on. So today matter and possibly a cosmological constant dominate the landscape early on because of the 8 to the minus 4 scaling. Radiation was the dominant constituent of the universe. Because basically, we didn't even matter like hydrogen, helium, lithium. These things were not there in the beginning of the universe. Those were made later. Let's introduce some numbers. Oh, okay. Here. See how wait a minute. What is EQ? Is that? Okay, I'm sure they'll energy density versus scale factor for different constituents of a flat universe. Shown are non-relativistic matter, radiation, and a cosmological constant. All are in units of the critical density today. even though matter and cosmological constant dominate today, at early times the radiation density was largest. The epoch at which matter and radiation are, that's right. The epoch of the universe at which matter and radiation are equal is A equal. I see. Okay. So the EQ is just equal. Where it was the same. Okay. So the expansion is often written in units of velocity per distance. Present measures of the Hubble rate are parametrized by h, defined by capital H naught, Hubble rate, is equal to 100 h kilometers per second per megaparsec. So notice how megaparsec is the unit here. So this is going to be a very large distance scale type thing. Because, parsecs and kiloparsecs are more common in astronomy, but in cosmology, we consider megaparsecs. That's a very large distance scale. This small h has nothing to do with Planck's constant. The astronomical length scale of a megaparsec is equal to 3.085 times 10 to the 24 centimeters. So that's a megaparsec. Current measurements set this small h to be 0.72 plus or minus 0.08. So, wow. The predicted age for a flat, matter-dominated 2/3 H naught type of universe is then of order 8 to 10 gigayears. So that's where the 13.6 billion year age comes from. The current best estimate for the age of the universe is around 12.6 gigayears with a 95% confidence level, lower limit of 10.4 gigayears. So this test suggests that a flat matter-dominated universe is barely viable. You will show in exercise 2 that the age of the universe with the cosmological constant is larger. So they did this without the cosmological constant. In fact, one of the original arguments in favor of this excess energy was to make the universe older. Oh, I didn't know that. As in, I probably knew that, forgot. Newton's constant is the usual constant. This together, okay. So now we have a new equation for the critical density, given that we have this age and the constant that we knew about already. An important ramification of the higher densities in the past is that the rates for particles to interact with each other, which scale as the density, were also much higher earlier on. Ooh, look at this. Basically, these are the different things you could have. Weak scattering of neutrinos, Compton scattering of photons, and electron cooling. Rates as a function of the scale factor. When a given rate becomes smaller than the expansion rate h, that reaction falls out of equilibrium. So depending on the temperature of the universe, different types of reactions may or may not be happening at that time. So if we skip this part, what do we miss? Because there's a lot of equations here. When the temperature of the universe was greater than several MeV over Boltzmann constant, the rate for electrons and neutrinos to scatter was larger than the expansion rate. Oh, wow. So lots of things were happening when the temperature was greater. Let me, my tea is very cold now. Let me warm it up and have it. Take a little bit of a rest here, and we will continue. So, basically, from Einstein's equations and some of the measurements that they made, they're able to kind of estimate how much of the various interactions were happening at what times in the early universe, because they kind of know the temperature at that time and what things would have what types of interactions would have dominated basically at that time, which is really cool. It's like you can learn so much. That's awesome. Okay, I'll be right back. This is cosmology. It's so very cool. Whoops. Depending on your temperature, before the universe could double in size, a neutrino scattered many times off background electrons. All these scatterings oh my god. Basically, before the universe expanded further, because it's expanding with time, much went down because the environment was completely different. Sometimes I think, like, what is outside of the universe? Does that make sense? So, so before the universe could double in size, a neutrino scattered many times off of the background electrons. All these scatterings brought the neutrinos into equilibrium with the rest of the cosmic plasma. This is but one example of a very general, profound fact. If a particle scatters with a rate greater than the expansion rate, that particle stays in equilibrium. So basically, if the universe is expanding and it has an expansion rate, but the particle scatters more than that, then basically it's going to have a lot of opportunity, right, to do this, and it stays in equilibrium. Since rates were typically quite large, the early universe was a relatively simple environment. Not only was it very smooth, but many of its constituents were in equilibrium. Later on in chapter 2 here explores some manifestations of the equilibrium conditions, while chapter 3 touches on several cases where equilibrium could not be maintained because the reaction rates dropped beneath the expansion rate. Oh. Okay. So in 1929, Hubble first found that distant galaxies are in fact receding from us. He also noticed the trend that the velocity increases with distance. This is exactly what we expect in an expanding universe, for the physical distance between two galaxies is d equal to ax, where x is the co-moving distance. In the absence of any co-moving motion, the relative velocity is therefore equal to capital H times d. Therefore, velocity should increase linearly with distance, at least at low redshift, with the slope given by h, the Hubble constant. Hubble's constant can be easily extracted. There's a figure here, blah, 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 blah. Okay, the Hubble diagram is still the most direct evidence we have that the universe is expanding. So this Hubble diagram right here See, is the most direct evidence we have that the universe is in fact expanding. Current incarnations use the same principle as the original. Find the distance and the redshift of distant objects. Measuring redshifts is straightforward. The hard part is determining distances for objects of unknown intrinsic brightness. So the question earlier is being answered now. One of the most popular techniques is to try to find a standard candle, a class of objects which have the same intrinsic brightness. In any difference between the apparent brightness of two such objects, then, is a result of their different distances from us. This method is typically generalized to find a correlation between an observable and intrinsic brightness. For example, Cepheid variables are stars for which intrinsic brightness is tightly related to period. The Hubble Space Telescope measured the periods of thousands of Cepheid variables in galaxies as far away as to 20 megaparsecs. So basically, they're doing all of this type of stuff to figure out that the distances are growing. With distances to these galaxies fixed, 5 different distance measures were used to go much further, as far as to 400 megaparsecs, and the 3 curves. Okay, 3 curves. What do these show? Oh, they have various ways to figure out this candle thing. I simply point out that the expression depends on the energy content of the universe. The 3 curves depict 3 different possibilities: flat, matter-dominated, open, and flat with a cosmological constant. The high redshift data are now good enough to distinguish among these possibilities, strongly disfavoring the previously favored flat, matter-dominated universe. The current best fit is a universe with about 70% of the energy in the form of a cosmological constant or some other form of dark energy. So because they have all these different models of the universe, and then you also have data, basically the model of the universe that fits the best is the one with is the one with the cosmological constant, which gives us dark energy, unfortunately. So yeah, I wish, right, if the flat matter-dominated universe was fine, then we could have been okay, but it's not. No, the current best fit is a universe with about 70% of the energy in the form of a cosmological constant or some other form of dark energy. So that's what it is. A lot of people just think of it as the cosmological constant. It would still beg the question what the cosmological constant really means. But some people are less perturbed by dark energy because they think of it as something, I don't know, something intrinsic to the universe. They don't necessarily think of it as, because and I mean, it does come out of this cosmological model and whatnot, you know. So in that sense, some people think of it as maybe not even a thing. I don't know what to say. It's yeah, I don't know. Hopefully this cosmological model is good and it makes sense to fit it with the data. When the universe was much hotter and denser, when the temperature of order MeV, there were no neutral atoms or even bound nuclei. Ooh, right. So now we're talking about nucleosynthesis. So this whole nucleosynthesis thing and getting elements only happened later on. We will now read about the Big Bang, where you will see that certain conditions had to happen first before we can even really get elements. I am tired because this material is hard. This is hard. Thank you for joining. This is some hard stuff, but hopefully it's helping. We can talk about this again and again too. This is just from this book. We will reference more books. We will do this more and more. So not to worry. But Big Bang nucleosynthesis basically says that there were no neutral atoms or even bound nuclei when the universe was much hotter and denser, because that would have been impossible. The vast amounts of radiation in such a hot environment ensured that any atom or nucleus produced would be immediately destroyed by a high energy photon. So basically the photons were going nuts during the Big Bang era and not really letting elements and things like that form much. That's a much later thing. So as the universe cooled well below the binding energies of typical nuclei, light elements began to form. So you can imagine, even to form a helium atom, you need some peace and quiet. Knowing the conditions of the early universe and the relevant nuclear cross sections, we can calculate the expected primordial abundances of all the elements. So they even calculated estimates of the primordial, as in the very early days type of abundances, as in how much of this stuff was there, type of thing. And this is called BBN, Big Bang nucleosynthesis. Can somebody like the live so that I could get 10 likes? At least. The boxes and arrows, whatever, they show the estimates for the light element abundances. That's okay. I can show it to you later. These are consistent with the predictions, and this consistency test provides yet another ringing confirmation of the Big Bang. So because they were able to confirm their prediction of how much of the stuff there should have been around the Big Bang, they basically believe in the Big Bang. The measurements do even more though. They do even more. The theoretical predictions, which we will explore, depend on the density of protons and neutrons at the time of nucleosynthesis. The combined proton plus neutron density is called the baryon density. Ooh, since both protons and neutrons have a baryon number 1, and these are the only baryons around at the time. So there's this new word now called baryon. Cosmologists like it. Thus, BBN gives us a way of measuring the baryon density in the universe. Basically, they're coming up with a number for proton and neutron density because they love densities. Since we know how these densities scale as the universe evolves, because we had that equation from earlier, they fall as a to the minus 3, we can turn the measurements of the light element abundances into measurements of the baryon density today. In particular, The measurement of primordial deuterium pins down the baryon density extremely accurately to only a few percent of the critical density. Ordinary matter, baryons contributes at most 5%. Yay! Of the critical density, since the total matter density is almost certainly larger than this, direct estimates give values of order 20 to 30%. Nucleosynthesis provides a compelling argument for non-baryonic dark matter. So this is another compelling argument for dark matter. Yay! Coming from Big Bang nucleosynthesis. So we talked about dark matter evidence. So you see how some people think that we're crazy, that astronomy, physics people are just crazy. We're searching for dark matter for no freaking reason. But there is compelling evidence of dark matter not only from an astronomy point of view. We talked about the astronomy point of view with the orbital speeds going nuts at distances, at large distances from the center of the galaxy, of our own galaxy, and how that was not expected, blah, de blah, de blah. And that's an astronomy evidence of dark matter. But there is also a cosmology evidence of dark matter, which is to do with Big Bang nucleosynthesis. They have figured out this whole matter density thing, and they've also figured out how much of the normal stuff there would have been, the baryon stuff, the you and me stuff there would have been at that time, and it does not account for all of the matter density. So that too is a sort of an evidence for non-baryonic dark matter. So basically, that is also to say that dark matter is not protons and neutrons. It's not made of ordinary matter. Bummer, but further evidence that this is indeed a problem. The deuterium measurements are the new developments in the field. These measurements are so exciting because they explore the deuterium abundance at redshifts of order 3 to 4, well before much processing could have altered the primordial abundances. Ooh, the primordial abundances are kind of important. They're very important. Basically, the abundances in the very early universe, like just after the Big Bang, is very importante, because not much more stuff has happened yet. It's almost like it's a good playground for us to understand how much of each thing there is in the universe. And later on, we know that it will evolve into more elements and stars and galaxies and all that shit. So it's kind of like primordial abundances give us information that the nowadays type of universe cannot. The basic idea is that the light from distant quasars is absorbed by intervening neutral hydrogen systems. The key absorption feature Hi, Callie. That's okay. Here we are, no worries. The key absorption feature arises from transition from the n=1 ground state of hydrogen to the first excited state, which is n=2, requiring a photon with wavelength of around 1200 angstrom. Since photons are absorbed when exciting hydrogen in this fashion, there is a trough in the spectrum at this same wavelength, redshifted by a factor of 1 plus z. This corresponding line from the deuterium should be shifted over by 0.33 times 1 plus z, and much less damped, since there is much less deuterium. So here it shows there are now half a dozen with detections precisely in the neighborhood shown in figure 1.8. Note that the steep decline in deuterium as a function of baryon density helps here. Even relatively large errors in D measurements translate into small errors on the baryon density. Wow. I'm not sure I follow this. I don't know where the 0.33 came from. If a cosmologist is watching the live, could you please say why there is a 0.33? I wish that Chris would see this live. Maybe I will share it with a professor of mine. Yeah, I don't know why there's a 0.33 there, but here's the pictures. Whatever. We kind of follow. Oh, whoops. The main problem here, the main takeaway here is that, if people are wondering, that is, the main takeaway here is that Big Bang nucleosynthesis gives us a density for baryons, which is the cosmologist nickname for protons and neutrons, because in the very, very early days, we didn't really have the elements because it was too hot then in the universe. But from that matter density, we can understand sort of, we can tally up the numbers. And we're seeing that whatever this density is for baryons is not really accounting for the matter density. We would need something else. And this is further evidence for dark matter, which is pretty strong of an argument for something like dark matter. Like because when there's astronomy evidence of dark matter, say for our own galaxy, that's very different. Our galaxy is not our galaxy is here now. We're here now. This is like a much later stage universe evolution type of thing. So if our galaxy has dark matter and our neighboring galaxies have dark matter, that's like, okay, it's a more current thing. But now we're talking about the beginning of the freaking universe. If there was dark matter in the Big Bang's nucleosynthesis time period, then that means that dark matter is just fundamentally something that was there even back then. And we don't know what it is. And that it's a thing. It's a thing, we don't know what it is, but it's a thing not just now, not just in our galaxy, not just in our neighboring galaxies, but it was a thing even back then. Wow. So anyway, then there's the cosmic microwave background. Boring stuff, but we'll go over it. Very important stuff. The CMB offers us a look at the universe when it was only 300,000 years old. So we talked about Big Bang nucleosynthesis. This is like very early universe, baby universe. But then when the universe is around 300,000 years old, so still very new, because at this time it's more like 14 billion years old, very old compared to before. And now we have galaxies, we have stars, we have us, we have so much evolution of this universe. But back then things were simple, much more simple. And the environment was very different. Yash! Hi! Hello. So this cosmic microwave background radiation is from 300,000 years old, okay? It's when the universe was only 300,000 years old. Wow, so young. The photons in the cosmic microwave background last scattered off electrons at redshift of 1100. Since then, they have traveled freely through space. Wow. We're good. Can you like the live and give us 10 likes? It's been lonely. This live has had not many people, so I've gotten more and more insane. How are you? It's been so lonely. Cosmology has been lonely. I love it, but people like cosmetology more. And look at us. I like the life. Thank you. Thank you, my friend. Me too. Thank you. So, this is some really interesting stuff. These photons, from when the universe was only 300,000 years old, scattered off of electrons. Because remember, photons and electrons have been friends for a long time. Um, I just came back from school too. Oh, good. Wait, isn't today your Saturday? Wait, what day is it today? It's Friday here. You had school today? शनिवार को भी स्कूल था. आज आपका सैटरडे है ना? So, anyway, right here is also a school. All days. Yes, today is Saturday. Wow, Yash, you go to school on Saturday too? That's a lot. That's cool. So, because photons and electrons have been friends for a long time, but these photons that are being measured as part of the cosmic microwave background, they would have last scattered off of electrons at a redshift of 1100. Since then, they have traveled freely through space. So their last encounter was a while ago. And since then, they've traveled freely through space. When we observe them today, they literally come from the earliest moments of time. They are therefore the most powerful probes of the early universe. So getting these photons from the early universe is literally so amazing, because it's almost like they're like pure. They're from those early days. We will spend an inordinate amount of time in this book working through the details of what happened before the epoch of last scattering, and also developing the mathematics of the free streaming process since then. A crucial fact about this history, though, is that the collisions with electrons before last scattering ensured that the photons were in equilibrium. That is, they should have a black body spectrum. So they were in equilibrium, and they give us a black body spectrum. So this black body radiation we found because we kind of might have looked for it, and we did find it. So there's a remarkable agreement between this prediction of Big Bang cosmology and the observations by the FIRAS instrument aboard the Kobe spacecraft. We have been told that the detection of the 3 Kelvin background by Penzias and Wilson in the mid-1960s was sufficient evidence to decide the controversy in favor of the Big Bang over the steady-state universe. So this is confirmation about the Big Bang. Measured the radiation at just one wavelength, even if Penzias and Wilson, they measured it at one wavelength, even their one wavelength result was enough to tip the scales. The current data depicted in which figure 1.10. Ooh, this one. Wow. Should send skeptics from the pages of physics journals to the far reaches of radical internet chat groups. Oh my God. The most important fact we learned from our first 25 years of surveying the CMB was that the early universe was very smooth. No anisotropies were detected in the CMB. This period, while undoubtedly frustrating for observers searching for anisotropies, solidified the view of a smooth Big Bang. We're now moving on. We have discovered anisotropies in the CMB, indicating that the early universe was not completely smooth. There were small perturbations in the cosmic plasma. To understand these, we must go beyond the standard model. So there were like tiny whiny little perturbations in the early smooth universe. Wow. हमारा सैटरडे है लेकिन मेरी टीचर ने हमें काम में लिए बुलाया था. I literally just woke up. I'm in the UK. Yeah. Yes. Meet each other, Callie and Yash. Wow. So people looked for anisotropies in the CMB in this early smooth universe. And mostly it was difficult to find. But there are tiny little perturbations, which we'll talk about next. Wow. Oh my God. So I hinted above at one of these. Okay, the notion that there must be non-baryonic matter in the universe. Dark matter is a familiar concept to astronomers. The first suggestion was put forth by Zwicky in 1933. Dark matter can be found in galaxies with the use of rotation curves, probing the gravitational field. Indeed, a mismatch between the matter inferred from gravity and that we can see exists on almost all observable scales. Because of the limits inferred from Big Bang nucleosynthesis, the dark matter, or at least an appreciable fraction of it, must be non-baryonic. What is this new form of matter? And how did it form in the early universe? The most popular idea currently is that the dark matter consists of elementary particles produced in the earliest moments of the Big Bang. Oh my God. In Chapter 3, we will explore this possibility in detail, arguing that dark matter was likely produced when the temperature of the universe was of order hundreds of GeV. As we will see, the hypothesis that dark matter consists of fundamental relics from the early universe may soon be tested experimentally. So if they go back in time to the Big Bang period and pick up on and pick up on something to do with dark matter, that would be freaking amazing. Oh wow. The last decades of the 20th century saw a number of large surveys of galaxies designed to measure structure in the universe. These culminated in two large surveys, the Sloan Digital Sky Survey and the 2-degree Field Galaxy redshift survey, which between them will compile the redshifts of and hence the distances to 1 million galaxies. Are you sleepy? Yeah. And where are the other two kitties? They have gone upstairs to warm up the bed. Baji's giving me company. I'm gonna go join them. I think it's time for my bed too. To understand this structure, we must go beyond the standard model, not only by including dark matter, but also by allowing for deviations from smoothness. So these little deviations from smoothness that they talk about might be a further proof of dark matter. We must develop the tools to study perturbations around the smooth background of the standard model. We will see in chapters 4 and 5 that this is straightforward in theory, as long as the perturbations remain small. Well, Yash, we haven't seen you in forever, so tell us something. How is everything going with you? How was school? I think I'm done reading for tonight. I'm done studying for tonight. But I am a little perturbed by these perturbations. I want to know how they measure the perturbations, actually. Kind of want to go back to school now and study more cosmology. I'm drinking my warm drink. I think I should take a cosmology class. Hopefully, it'll be free. Maybe they need help. Yeah. Yeah, I don't know. I don't know about, well, we will read further, but I'm not really sure how they're finding the anisotropies. I think we will determine this next time. Oh God, that's right. Those the harmonics. They can probably find dark matter from the CMB. Look at Baji. Baji, are you awake now? Baji's awake. Good, I have a test on Monday. And now me and my class have to go to school on every Saturday till 10 to 1. Good luck on your test. Wow. Good luck. I don't understand. I don't understand. Time since the Big Bang by the value of the scale factor or by the temperature of the cosmic plasma. We know the temperature of the cosmic plasma. So it's a summary of this chapter. We can characterize an epoch in the universe by the time since the Big Bang by the value of the scale factor at that time or by the temperature of the cosmic plasma. For example, today A equals 1, 2 equals 14 billion, and the temperature is 2.725 Kelvin, which is pretty small. Shows the timeline of the universe using both time and temperature as markers. The milestones indicated on the timeline range from those about which we are quite certain, nucleosynthesis and the CMB, to those that are not as certain, more speculative, dark matter production, inflation, and dark energy today. So they kind of know the timelines of the CMB and nucleosynthesis pretty well, but they don't understand dark matter production, inflation, and dark energy. Oh. Shows the dominant component. Early on, most of the energy in the universe was in the form of radiation. Eventually, since the energy of a relativistic particle falls as 1 over A, while that of non-relativistic matter remains constant at m, matter overtook radiation. At relatively recent times, the universe appears to have become dominated not by matter but by some dark energy, whose density remains relatively constant with time. The evidence for this unexplained form of energy is new and certainly not conclusive, but it's very suggestive. The classical results in cosmology can be understood in the context of a smooth universe. I'm slowly lying down, becoming more and more horizontal over here. The classical results in cosmology can be understood in the context. Okay, so the CMB. Oh my god. So the CMB. No worries. So CMB, studying the CMB is going to be very important for He's saying that anisotropies in the CMB today tell us what the universe looked like when it was several 100,000 years old. So they are wonderful probes of the perturbations. So this CMB stuff and nucleosynthesis stuff from the from the estimates they have and picking up on the temperature and all that stuff is gonna be very, very important indeed. I don't think he's saying that but by some dark energy whose density remains relatively constant. I wonder if the cosmology people just made a mistake. But they couldn't have all made a mistake. Because it seems like this dark energy way of having the universe, it kind of flipped to being dark energy dominant. You know? So, yeah. Baji. Look at Baji's foot. Baji's kicking the phone. Baji. Baji, what do you think of dark energy? Baji. Baji says that dark energy is very confusing. And the universe wasn't always dominated by dark energy. And in fact, radiation was very important. But that even Big Bang nucleosynthesis is pointing towards dark matter. But that's different from dark energy. Baji, why do we need dark energy? Tell me. Quiz question. Baji, let's hold hands during this confusing moment. Come, Baji. Ho, 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 ho. Look at that stretch. Look at that stretch. Baji. Baji. Oh, oh no. There's a light. A light came on. I didn't mean to. I didn't mean to do that. Oh gosh. Oh good God. Okay. Well, there's a light. How do I make it go away? Oh my God. Oh gosh. Oh. Okay. 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 We're here. So I think we will continue more discussion next time. On this topic, for sure. Okay. Thank you for joining, everybody. We are falling asleep now. I think we will come back next time. Here, you can sleep with Baji. You can sleep with Baj. Ah! Everything's falling. Little Baji Baba. Hi, Baji. What is this person talking about? I'm looking at a very old reel I made, or not reel, a short. Someone is asking about that. 666 views. Goodness. Somebody's comment. Thank you, babies. Thank you for joining.